Hello, welcome back. We're going to begin a discussion of a very important molecule for living systems, the molecule's water. And so let's initially just talk about the molecule itself and some of its qualities, its makeup. And then you're going to find that we're going to discuss other aspects of water and also water-based solutions. Well, first of all, we refer to water as being a polar molecule. Remember, polar molecules are molecules that are composed of polar covalent bonds. And that usually means that we're dealing with atoms that are sharing electrons that have very different electronegativities. And in this case, we do. We have oxygen, which is an electron hog. Remember, I mentioned that idea before. And they hog the electrons that they're sharing with the hydrogen. And as a result, the water molecule has a negatively charged region, slightly negatively charged. That would be the region around the oxygen atom of the molecule. And we're going to have a slightly positively charged region, and that would be those two ends of the molecule where we have our hydrogen atoms. So we have a molecule that is a polar molecule. Remember, the quality of polarity simply means that the ends of something are different. Okay? And in this particular case, the oxygen end of the molecule is different from the hydrogen ends of the molecule. It's different in terms of there being a slight negative on the oxygen, slight positive on the hydrogens. Now, one of the things that this will do for the water molecule is it means that one water molecule will be able to attract other water molecules. If you think about it, the negatively charged portion, the oxygen negatively charged portion of one water molecule will be attracted to the positively charged hydrogens of other molecules. Remember what that forms? That's going to form that hydrogen bond, that weak electrostatic attraction. Now, of course, that could also happen between a nitrogen of some molecule and the hydrogen of a water molecule as well. Remember, oxygen and nitrogen are those two electron hogs we talked about that are the key ones that give rise to those polar covalent bonds. So we'd expect that when we have covalent bonds involving oxygen and hydrogen or nitrogen and hydrogen, that they're going to be polar, and that the oxygen or nitrogen portion of those bonds will be negative, partial negative charges. The hydrogen portion of those molecules will be slightly positive. So we'd expect that to be a perfect location for hydrogen bonding to form. Well, let's take a look at the water molecule quickly and see those features. Notice that what we have here is a water molecule represented with its single oxygen atom and its two hydrogens. We have our positively charged regions on the hydrogens. And up here at the oxygen, we would actually have two negative regions. In this particular illustration, they're just saying that the oxygen portion has a negative charge, but you could think of it as two partial negative charges. All right? If you think about it, we're talking about this unequal sharing of electrons and the same one with the other hydrogen, and that creates this negative region here and positive region here. Okay? So that unequal sharing of electrons. Now think about what that does to the water molecules. That means that they have the ability to form these hydrogen bonds. As a matter of fact, any one water molecule can form 4 hydrogen bonds with other water molecules. It makes the water molecules interacting with each other. Some people say that water is sticky, meaning that the molecules like to stick to each other, and the stickiness is due to this hydrogen bonding. So when we talk about this stickiness of water molecules, we're focused on this ability for hydrogen bonds to form between individual water molecules. Remember, hydrogen bonds form between molecules, not within molecules. If I'm focused on water molecules sticking to other water molecules, or any situation where I have hydrogen bonds allowing two of the same kind of molecule to stick to each other, then that's called cohesion. And water cohesion is an important property of water. Water molecules sticking to other water molecules with hydrogen bonds. Now, hydrogen bonding could also be responsible for two different kinds of molecules to stick to each other. Water might be attracted to ammonia, for example. As a result, if I have hydrogen bonds that are allowing two different kind of molecules to stick to each other, then the term for that is adhesion. So notice, cohesion and adhesion are both qualities that are related to hydrogen bonds forming between polar molecules. Hydrogen bonds between polar molecules. Now, think about what that does to a volume of water, a container of water. Because all the water molecules are being attracted to each other, we can think of the water as having surface tension. You've probably seen this. I mean, think about the water on a pond from the perspective of a bug. Bugs can walk right along the surface of the water. As a matter of fact, when their feet push on the water surface, it just sort of creates a little depression. It would be like me walking across a trampoline. You could say it this way. The mass of the bug is not sufficient to separate or break the hydrogen bonds holding the water together. The water has a surface tension. By the way, that's why drops of water form spheres. All the water molecules pull on each other, and they pull into the most compact form they can, which is a sphere. Now, me walking on the trampoline, of course, I don't break the bonds holding together the molecules of the trampoline. And so we could say, oh, those bonds that form the molecules of the trampoline have a greater force than the mass that I'm putting on them, the force that I'm putting on them. And so, in that sense, we could think of the water and the bug as being similar to the way in which I am associated with the molecular bonding that occurs in something like a trampoline. Now, also, I can remember as a kid, I used to love to pour my juice into the glass at the table when we were having dinner or something like that, and I'd keep pouring it in and keep pouring it in. You might have tried this. And you can actually get the water to come up, the fluid to come up above the surface of the glass. It seems as if it's sort of hanging over the edge of the glass, but not spilling out. Of course, as you pour more in, it will spill. But when it gets up to that point where it's sort of hanging over the edge of the glass, you want to think about, oh, I see what's going on. As the water molecules are trying to fall over the edge of the glass, all the other water molecules in the container are pulling on it with hydrogen bonds, holding it back. The surface tension of the water is keeping it from spilling over the edge. So, see if you can observe some examples of surface tension in fluids, waters, as you go through your everyday existence, your life. Look for those examples of surface tension and see if you can find some of them. What other properties of water are the result of these adhesive and cohesive properties? Well, one of the things we find is that water has a very high boiling point for the size of molecule it is. Usually, how much energy it takes to boil something is directly related to how big the molecule is. But water, for its size, because it's only 3 atoms, remember, has one of the highest boiling points. Well, think about what's going on. When water tries to boil, right, as water molecules gain energy and try to become a gas, not only do they have to gain enough energy to vibrate fast enough to become a gas, but they have to overcome all the cohesive forces pulling them back into the water. All their buddies are trying to hold them in. So this quality of having a high boiling point is another feature of water that's directly related to that hydrogen bonding, the cohesive properties of water. Now, in addition to this, water has a very low density when it freezes. What that means is that as water molecules slow down, imagine a container, if these are water molecules, imagine a container of water with the water molecules running around, bouncing, hitting into each other, moving relatively rapidly, occasionally forming some hydrogen bonds, but breaking those hydrogen bonds very quickly. On average, the water molecules can be fairly close to each other. But as I cool water and I slow down the molecules, as they start to move more and more slowly, begin to line up in a very regular pattern. Because of their hydrogen bonds, each of the water molecules gets an average distance from each other that's greater than when the water is moving faster. As a result, when water freezes, it becomes less dense. That's very odd. Very few things have that capability. And of course, it's important for living things. If I'm a fish living in a lake, I'm very glad that water gets less dense as it freezes. Because what does that mean? The ice will form on the top of the lake, and I'll be able to stay in liquid water underneath that throughout the winter and survive. Rarely does water freeze the whole way to the bottom of a lake or a pond. It can occasionally. Very cold conditions, very shallow bodies of water. But for the most part, the water at the bottom of the pond is going to be about 4 degrees Celsius. That's when water is at its densest. And the water that's colder than that is going to float to the surface as it freezes. So that means that organisms living in water environments are protected from these severe cold conditions. Water has a high heat of vaporization. Here's what that means. Imagine if I took some alcohol and smeared it on my skin. By the way, alcohol is a larger molecule than water. But think about what happens. I smear the alcohol on my skin, it evaporates very quickly. It turns into a vapor rapidly. It gains heat from my skin and turns into a vapor. Now think about that, because you probably realize that if I smear some alcohol on my skin, I perceive my skin as getting cooler as the alcohol evaporates and takes some of the heat from my skin with it. If I smear water on my skin, it will evaporate also, won't it? It will turn into a vapor, but it takes it much longer. And it takes greater amount of energy to get it to turn into a vapor. Well, think about what living things use as their primary cooling mechanism. Water, right? They take some surface of their body and they produce water on the surface, allow it to evaporate and carry away some of the heat of their body, primarily through sweating, but it also could be through the panting that dogs do off of the surface of their tongue. Or it could be what some rabbits, desert rabbits, do, and they lick their forelegs and let the saliva evaporate off of their legs. So lots of organisms use this quality of water to draw heat, take heat away from their bodies as it vaporizes, taking a high amount of energy for its molecular size. And finally, water is a wonderful solvent. As a matter of fact, some people call it the universal solvent, which means that there's lots of things that can mix with and dissolve in water. And it's mainly because of these charges that the water molecule has. Its ability to form adhesive forces on other molecules and get them to separate as they're placed into a water solution. So water is a wonderful solvent. Notice, in this one slide, we've talked about 4 different qualities of water that are all associated with its polar nature, its charge distribution, its ability to form hydrogen bonds, its cohesive and adhesive properties. Now, using water as a solvent means that I can make aqueous solutions. Those are water-based solutions. Now, a solution is simply a liquid that has something else mixed into it. And in a solution, the 2 components are the solvent and the solute. Now, the solvent is the agent that's doing the dissolving. And if we're talking about aqueous solutions, that solvent is always going to be water. In biological systems, in living things, in cells, we are water-based organisms. We're based on aqueous solutions. The material dissolved in the water is called the solute, and that can come in a variety of forms. Here's one example. Sodium chloride, salt. Do sodium chloride crystals dissolve in water? Is water a good solvent of this compound that is held together by ionic bonds? It certainly is. Notice how water can help sodium chloride come apart when it goes into solution. Sodium ions, look what happens to them. Their positive charges are attracted by all the negative charges of the water molecules, pulling on those sodiums, helping them to come apart, leave the crystalline structure of the sodium chloride. And the chloride ions also want to mix with the water. Notice they have negative charges. The positive charges of the water molecules pull on those chloride ions and help them to mix with the water. So, water molecules, water itself, very, very good solvent. many things can dissolve, mix easily, or dissolve in water. Matter of fact, we're going to talk about this solvent ability of water in much more detail in a couple other videos. It's a key feature of living things. We are aqueous environments. We are based upon water solutions. Now, things that are solutes that mix well with water, things like sodium chloride, that go into solution well, things that are able to dissolve or mix with water, are said to be hydrophilic. Those things that don't like to mix with water are said to be hydrophobic. All right, now think about this for a moment. If you think about the quality that we talked about that allows water to help things mix or dissolve in it, then one of the things that you should be thinking about is, gee, hydrophilic things must be things that have some kinds of charges associated with them. Because notice, all that mixing with water, the ability of water to pull on things or hold on to things or cause them to separate in water, was due to the charges of the water molecule interacting with the charges of the molecule that was mixing with the water. So I would expect that hydrophilic things would have one thing in common. Somehow they're going to have charges. As a matter of fact, I would expect hydrophilic things to have one of two qualities. Either they have polar covalent bonds in them. All right, remember that would give them charges, wouldn't it? Or they're going to be held together by ionic bonds. So hydrophilic things I would expect to be things that have charges. Polar covalent bonding charges, ionic bonding charges. Well, what about these hydrophobic things then? Oil doesn't mix very well with water, does it? No, it doesn't. They separate from each other. So if I analyze oil, what would I expect to find? I'd expect to find that it doesn't have very many charges on it. Right? Fewer the charges, the less able it is to mix or dissolve in the water. So that would be a quality I'd expect to find on basically all hydrophobic things. Now, we're going to see that there are molecules that are both hydrophilic and hydrophobic. You know, one end hydrophilic, one end hydrophobic. And as you might expect, I'd expect one end, if it is hydrophobic, to not have very many or any charges, and another end that's hydrophilic to have charges. Another way to think of this would be, I might expect one end of the molecule to be non-polar, right? Not have charges. Another end of the molecule to be polar and have charges. And you're going to see that when we talk about some of the organic molecules, we're going to refer to them as being amphipathic. Amphipathic means both hydrophilic and hydrophobic. So this is an idea we'll come back to again. Remember, if we're organisms that are based on aqueous solutions, the hydrophilic or hydrophobic nature of molecules is going to be very important to us, understanding how they work within cells, how they're used by cells. Okay? Important idea, this idea of aqueous solutions, water as a solvent. All right, so let's consider some of these characteristics of water. It has this quality of polarity, right? It's a polar molecule, negatively charged portion, positively charged portion. Water molecules are very good at forming hydrogen bonds. The hydrogen bonding nature of water allows it to be both adhesive and cohesive. Adhesion with other molecules, cohesion with the same water molecules. Water is a wonderful solvent that solutes can be mixed with or dissolved in. As a result, water is the primary component of the solutions found in cells. And we'd expect that we could classify molecules as either being hydrophilic or hydrophobic in relation to their ability to mix with water or not mix with water. Remember, we said the key idea was associated with whether they do or do not have charges. Keep these things in mind. We'll be talking about water a lot this semester, so these should be ideas that we hit on more and more as we go along this semester. Thanks very much. Talk to you later.